Previously, we looked at the RIS 1.0 and 2.0, and today we look at the expansion set Exploration Mars. Due to the limited number and linear format of the missions, we will go through all of them and show all the design briefs rather than looking at the box and the parts, etc. As usual, we ran the software on our Windows XP laptop. The installation in the background is running at 4x speed.
Over the years, the Space Academy has launched many missions to Mars. These brave explorers discovered fascinating information about Mars. Their discoveries have even helped to change the way we understand our own planet. The Space Academy was formed by the nations of Earth. Its mission, to train a new generation of explorers. Today, a new cadet enters the Academy, ready to accept the challenge of exploration.
Come in, Mission Control. Hello? Boost this signal. Mission Control needs to fix this darn thing. There you are. A bit of audio degradation with the signal's uplink. That's better. Glad to have you on board, Specialist. You've got Mission Commander Keller here. I'm going to be giving you a helping hand in the upcoming missions. I'm currently on a geosynchronous orbit above your position on Earth. You'll enter commands on your terminal down there, and I'll patch them through to the lander and rover up on Mars. You manage the machines, I'll manage the uplink and schedule. If you need additional information, then we have a library for you to look at. Got that, Specialist? To get started, you need to select a mission. The missions are listed down along the left side of your screen. Seeing as this is your first time here, let's start with the Pioneer mission. That should settle you in nicely. Also gives us a chance to work out any kinks. If you got a camera attached to your PC, you can undertake 2 additional camera missions. If you don't have one, don't worry. There's plenty to do in the meantime. Okay, Specialist, select the Pioneer mission and let's get started. Okay, you've selected Pioneer. A good choice to learn the basics. In this important mission, you'll design, build, and operate a Mars lander. But first, we need to build what is known as a Mars Yard. A Mars Yard is a simulated Martian terrain. Click on Mars Yard to proceed. It's time for you to build your own Mars Yard. Your yard should simulate real features that you might encounter while exploring the red planet. Create a Martian landscape that contains different types of terrain and obstacles. Later on, we'll be designing rovers. We'll need some interesting objects for them to go around. Once you are done constructing your Mars Yard, you'll need to enter your results into your mission log. You'll use your log in all your missions to record your progress and data. Click on Log to move on.
While we did initially plan on making a Mars yard with various Lego elements, we filmed this video over several weekends and we did not have a place to keep fixed setup. We ended up using ad hoc obstacles for all the tasks that required them.
Okay, if you have completed the Mars Yard task, you should have an environment where we can run our missions. The next step is to build a Mars lander. The lander is your main base of operations on the surface of Mars. It serves as your platform for operating equipment, monitoring sensor data, and controlling rovers. You'll find detailed instructions for how to build a lander in the Constructopedia. Once you are done, click on the log button to enter your results and move along. Good luck, Specialist.
For the lander base and the upcoming robotic arm, we built the models as shown in the Constructopedia. The former features no moving parts at all, and the latter features a fairly typical under-actuated gripper.
For this task, you need to add a robotic arm to your lander. Arms are important for picking up objects from the surface and taking samples from returning rovers. I'm downloading a video feed to you showing a prototype arm that's been developed over at the Academy. It's built with two motors. One motor lets the arm rotate left and right. The other motor raises and lowers the arm. It's also got a grabbing mechanism at the end for picking up objects. Your Constructopedia contains building instructions for this arm. Once you've built your arm, click on Program to go to the next step.
So there were a number of challenges getting this to work properly. First off, it doesn't tell you which way the wires are supposed to go, so there's some trial and error involved there. Secondly, this claw can only pick up very light objects, like an empty can, but of course, when you lower it onto a light object, then it will sort of push the light object away, and you won't get a good grip on it. So it has to be resistant to rolling away, and hence there are two tires behind this, so it can't roll away, it can't rotate, and we can get a good grip on it.
The rover needs two motors, one for driving wheels on the left side and one for driving wheels on the right side. It should be capable of driving forward and backward as well as turning left and right. The wheels are geared down to turn very slowly so that you can control the rover movements with a high degree of precision. Your Constructopedia contains building instructions for two different rovers. I strongly recommend you build Rover 1 using the long black wires. Connect outputs A and C on the RCX to the left and right side motors of Rover 1. Click on Program to continue.
For this next challenge, we decided not to use the Constructopedia design.
So we've built a four-wheeled rover, and there's a few things we've incorporated here that actually exist in regular Mars rovers. The first is to use big wheels to give yourself some more ground clearance to start with. We used a worm gearing for the drive to make this run very slowly. And you may notice a bunch of strange stuff going on. And the strange stuff going on is to implement passive suspension. Unlike spring-loaded suspension, passive suspension, the objective is to keep all the wheels on the ground. So the body is actually hinged. You can see the two sides are hinged like this. So if I raise this wheel, the robot is flexible, and so all of the wheels will stay on the ground. There's a mechanism in here because if you just pin these two sides to each other, the RCX would spin over and fall on the bottom. So there's a core, and we'll show how we built that separately here, which forces when one side goes up, the other side goes down, up, down, up, down, up, down. And so when they're balanced, the RCX has no place to go, and it can't rotate up or down. So one feature of this passive suspension is that it averages out the movement. The RCX will rotate half as much as either side, and therefore it'll go up and down half as much as the tallest obstacle a wheel hits. So take a look here. I'm going to raise this wheel by one hub, and the RCX goes up maybe half a hub's worth, if we can stack that. So this is the core that balances the two sides of the rover. So remember from this that the two sides need to be able to rotate freely relative to each other, but they're interlinked such that the body stays level. And so to do that, instead of using a linkage, because there's no ball joints in the RS sets, we're using basically a giant differential instead. And so these two sides are linked to each other, and there's some crown gears in there to keep them turning opposite. And so this will plug into, each side will plug into one half of the rover, and therefore if one side wants to go up, the other side has to go down, and the body will be held level. So now we have the two sides. I can plug them into the core, so each side is like that. And so I can't press this gear down directly like this because it will cause them to rotate together. And so what I want to do is hold this steady and hold these level to each other. So actually I'm going to connect them now. So now the 40-tooth gears are forced to be at the same angle temporarily. And then I'm just going to drop this gear in. And now, since I don't care about the angle of this, I can actually drop it in wherever, but so long as, oh, not wherever, this actually has to stay level for every gear to be supported on two sides. So I'm just going to drop this in now. It's stuck, drop that in, and now I can assemble this side. And now, when I take the pins out, the assembly will turn freely, and you can see that the 40-tooth gears are aligned with each other.
Now, Specialist, your mission is to collect and store samples for future missions to pick up and return to Earth. This is called a precursor to a sample return. At a later date, another mission will come and pick up this sample and return it to Earth. To do this task, you need to add a dozer blade to the front of your rover. Check out the special features section of the Constructopedia to see building instructions for this. The samples can be anything the rover can push back to the lander. The team back at the Academy tends to use Lego bricks for their test.
Both the rover test exercise and the sample return challenge use the same basic idea, so we only did it once. The rover needs to navigate a path with dead reckoning, driving and turning based on time intervals. This is tedious to set up, as coding a path requires considerable trial and error, and it's easy to mess up as the rover needs to have the exact same starting position and orientation each run. For the first time in an RIS challenge, we don't get any sample code, probably due to the potential variety of individual users' Mars yards.
Your first task is to build a rover capable of driving over an obstacle without tipping or getting stuck. Use the RCX brick as part of the rover body and include 2 motors for skid steering. Don't forget what skid steering is. It's turning in place. To do this, the wheels on each side turn in opposite directions. I recommend that you use the Rover 1 design from the Constructopedia.
Here we see how well our rover design handles various obstacles. Generally speaking, this design will do better with large obstacles due to improved suspension, while the Constructopedia design may do better with small obstacles due to more wheels. For the course itself, we drove back and forth over a book, as shown in the design brief with Dead Reckoning.
All right, Specialist. Are you ready for something a little more challenging? With this task, you will navigate between obstacles using touch sensors. First of all, install 2 touch sensors on the front of your rover. You may also want to add a bumper in front of each sensor to help it detect objects in the rover's path. Check out the special features section of your Constructopedia for ideas on how to add touch sensors and bumpers to your rover. For best results, the bumpers should extend out past the left and right front wheels. Click on the Program button when you're done.
Now we add sensors to allow the rover to navigate around obstructions. It should keep going in the same direction after avoiding an obstacle, but this only works for objects of limited size and shape. If a sensor gets re-triggered during the avoidance routine, it won't finish the first routine after completing the second.
In this task, we're going to use mission control to operate your rover directly from your computer. However, if you tried to control a rover on Mars, it would take the uplink as long as 20 minutes to arrive. Position your IR transmitter so the signals can reach the largest possible area of your Mars yard. Placing the transmitter on the edge of a desk or table may improve your range. Click Operate to continue.
The software controls for the rover feel absolutely awful. All the inputs have horrendous amounts of lag. Perhaps this makes for a realistic Mars rover driving experience, but it also makes for a pretty terrible Technic robot driving experience. That being said, we don't think they did this intentionally, and more on that in a future video.
Okay, Specialist. I'm very impressed with your achievements so far. You've made one fine planetary explorer, but we're not done yet. In this task, the rover will automatically navigate itself towards a light beacon. A beacon is a kind of marker that a previous mission would leave behind. This would allow a rover to collect samples that have been stockpiled at a central pickup point, like a lander, for instance. For this task, you'll need to attach a light sensor to the front of your rover. If you have a flashlight handy, you can use this as your beacon. This beacon will be what your rover looks for, as long as it's switched on, of course. Click on Program to move on.
So we're testing two programs to figure out which one is better at finding this light source. In this program, we're going to drive forward for 5 seconds, then look for the light source, then repeat that process, and hopefully this recalibration helps the robot home in on the light source. In the other, we're just going to find light once and drive straight at the light source.
So that's the last of the Exploration Mars challenges. At least those we can do without a camera. Fortunately, we have found a camera, and we will take a look at it in the aforementioned future video. On that note, this is the end of this video. Please consider subscribing if you like what we do, and have a nice day.
As you thought it would? For an extra degree of difficulty, add touch sensors that will allow you to go around obstacles that are in the way of your rover.